Dear students, in this section we are going to learn how to calculate force on a dipole placed in non-uniform electric field. Suppose a dipole is placed in uniform electric field. Here you can observe this dipole is placed along the electric field lines. That means the dipole moment vector and electric field lines are making 0° angle. This is the negative charge of the dipole, this is the positive charge of the dipole. In dipole, charges have equal and opposite magnitude separated by a small distance. Electric field is E. That means the negative charge will experience force in the leftward direction. It will have the magnitude QE, and positive charge will experience the force same magnitude, that is QE, but in the rightward direction. That means net force experienced by this dipole will be 0. That means translational equilibrium condition. Also, net torque acting on the dipole in this condition is also 0. That means rotational equilibrium condition. Now, what happens if we rotate dipole at certain angle like this, theta degree, with respect to electric field lines? Dipole moment vector is making theta degree with respect to electric field lines here. Here also we can observe the negative charge and positive charge both will experience the equal magnitude force, but in opposite direction. That means net force on the dipole will be 0, but net torque on the dipole will not be 0. That means dipole will be in translational equilibrium condition, but not in rotational equilibrium condition. But one thing is common in both scenario, that is no force experienced by the dipole. Now we can say no force experienced by dipole in uniform electric field. Now let us place the dipole in non-uniform electric field like this. You can observe here at position of the negative charge, the density of the electric field lines are less, and at the position of the positive charge, density of the electric field lines are more. That means the electric field intensity at the position of the positive charge is greater than the intensity of the electric field at the position of the negative charge. That means the force experienced by the positive charge in the rightward direction will be greater than the force experienced by the negative charge in the leftward direction. That means in this condition dipole will experience net force. Okay, that means we can say dipole may experience force if it is placed in non-uniform electric field. Now let us calculate this force. Okay, so for calculating this force we need to calculate the potential energy associated with the external field. Okay, so let us write this potential energy, and we have the expression for the potential energy for dipole placed in external electric field. We have the formula U equal to minus P dot E. This is the expression for calculating the potential energy of the dipole placed in external electric field. P is the dipole moment and E is the external electric field at the center of the dipole. Okay, and if we are interested to calculate the force, because we know the potential energy is associated with the conservative field, that means force acting on the dipole can be calculated by taking gradient of this electric potential energy like this. So force on the dipole should be equal to negative gradient of the potential energy. Okay, if field is one dimensional, suppose vector field is one dimensional, so we can write Fx. Suppose electric field is only restricted along the positive x direction, you can say x direction, so we can write Fx equal to derivative of u with respect to x, negative derivative of u with respect to x. So force on the dipole will be this one. Okay, and you know u equal to minus P dot E. So here we can write this is P dot minus minus will be positive, because this is u with the negative sign and here is also negative sign, so this will be positive value. So the force should be equal to P vector dot E del E by dx, and in I direction. And similarly, suppose we have the three-dimensional field. For three-dimensional variation of the field, we can write F vector equal to del U by dx del x I cap and del U by del y j cap plus del U by del z k cap. Okay. Now let us take few illustrations. Through coming illustration, we are going to consolidate this concept. So, let us move to illustration number 1. In this illustration, it is given an electric dipole with dipole moment P. It is placed near a long line charge of linear charge density lambda as shown in the figure. This is the dipole having dipole moment P vector. This is the infinite long wire having charge density lambda per unit length. Okay, and this dipole is placed at a distance small r from this wire, and here we need to find the force acting on the dipole. Okay, so let us make the situation to the next page, and we know if we want to find the force acting on the dipole, we need to find the potential energy of the dipole associated with the electric field of the long wire, right? And we know the potential energy of the dipole and wire system is given by the formula U equal to minus P dot E, right? Here P is the dipole moment of the dipole and E is the electric field generated by the long wire. And we know this long wire will generate the electric field at the center of the dipole in the rightward direction like this. This is the E vector. You can observe here this electric field generated by the long wire and dipole moment both are in the same direction, and we know the magnitude of this electric field also. This is equal to lambda divided by 2 pi epsilon naught r. Okay. Now we can substitute the value of P, substitute the value of E, and we know the angle between these two vectors is 0 degree. So here we can write P multiplied by lambda divided by 2 pi epsilon r multiplied by cos 0. Okay, cos 0 equal to 1. So this value potential energy will be equal to lambda divided by lambda P divided by 2 pi epsilon r. This is the potential energy with negative sign. And here one thing to be noted, potential energy of the system is negative. That means the system has the negative potential energy. That means the dipole will attract toward the wire. There will be force of attraction of the dipole toward the wire. Okay. Now let us calculate the magnitude of the force. As we discussed in the theory part, the force acting on the dipole should be partial derivative of U with respect to R, okay, with negative sign. So here we can write force between the wire and dipole equal to minus del U by del R, and direction, you know, we can consider this rightward direction as the x direction. So the force will be associated with the I cap unit vector. Okay. Now we can make the partial derivative. That means we need to differentiate this function with respect to small r. You can observe here lambda P divided by 2 pi epsilon r are the constant term. That means the derivative of r to the power minus 1. R to the power minus 1 have the derivative value equal to minus 1 upon r square. So here we can write this term, the derivative lambda P divided by 2 pi epsilon naught, and this is minus 1 divided by r square I cap. Okay. Now we can rearrange this equation like this. So this value will be P lambda divided by 2 pi epsilon naught r square I cap, and as we discussed, the potential energy is negative, so force is attractive, and we can observe here through this vector equation the force acting on the dipole is in the negative x direction or leftward direction. So we can say the force on the dipole will be attractive toward the leftward direction. Dear aspirants, Cengage India has launched the new edition of our JEE Advanced Physics books. Please visit www.cengage.co.in to buy a copy. You can also buy the books from Amazon or Flipkart.